right, folks, here we go. We have just finished exploring the two outermost planets, and personally for me, I would consider them both planets, Pluto and Eris. If I had my way, and if we went by the definition that you came up with, we'd have an even 10 planets right now, and they would include those that you see here. But we are finished with our solar system. It is time to turn on the deep blue looking really cool jet boosters and head off away from our solar system. There we go. And if we travel fast enough and far enough, we look back at our solar system, and it is but a speck in our viewfinder. And we find ourselves, when we look around, among the stars. So you can write stars for your notes today. Thank you. All right, guys, we got to keep the volume down now. When I was in high school, if you said stars, it meant something else. The Resident Evil games were in full swing when I was in high school. They were huge. So just thought I'd throw that up there. Some history about stars. Go ahead and write down this whole slide. This is kind of an interesting piece of history here. Back in the day, when people looked at the sky, what they thought is they thought the Earth was surrounded by this massive, massive dome. And that on the other side of that dome was heaven. And they thought that stars were tiny little holes poked inside that dome, so that when you're actually looking at a star, you're getting a glimpse of heaven. Kind of an interesting way of thinking about it. You can see on this picture, they're imagining somebody reaching the edge of this dome and looking at heaven beyond it. I guess that's what they thought heaven looked like. So yeah, make sure you know the historicalness of that. So if we're going to figure things out about stars, primarily today, what we're going to be doing is figuring out how to classify them and figuring out how to figure how far away they are. Because when you look up at the sky, all those stars, they're a long ways out there. And you can't exactly take a meter stick to go out and measure how far away they are from the Earth. So we need different pieces of information to make that happen. What we're basically doing today is we're going to take a look at what we would call astrophysics. And it's just a one-day thing. We will spend time later looking at how stars work, what happens when they die, and things like that. But today it's mostly about looking at what we see in the sky and ultimately using it to find how far away those stars are. I had to do this big process when I was doing my research in astronomy when I had some papers published. So I just thought I'd walk you through that a little bit. Basically what this chart means is that when you look up at the sky, you can observe several things. One thing you can directly observe is the apparent magnitude of the star, how bright it looks. And that's halfway there to figuring out the star's distance. The rest of the way is figuring out a bunch of other things with fancy scientific equipment, ultimately to get you its absolute magnitude, how bright it would look from a specified distance, and using those two pieces of information, you can figure out how far away it is from us. So, we're going to take a journey through this, and first start with this apparent magnitude. So, in terms of a star's apparent magnitude, in order to figure out how bright it is, all we do is we point something at it, and the light coming in registers as a certain number. And that number is basically what its apparent magnitude is. In terms of definitions, write down apparent magnitude and that first bullet point, please. You don't have to write down the subpoint, just the first one. There's actually a pretty well-known constellation in this picture somewhere. Can anybody pick it out? Anybody at least point me to where it might be? Right here?
Yeah, I don't know.
This is a constellation. Any guesses on which one it is?
Wait, hold on.
All right. Owen got it. Yep.
I found Taurus.
Yes, you did. You can find Orion. You can find Taurus. So, yeah, this is Orion right here. The three stars you see in a row represent his belt. These are his hands and feet, obviously. And there's actually some interesting galaxies down there. But Orion is something that comes up in the wintertime, so it's very easy to see these days and going forward into the colder months. In terms of apparent magnitude, we measure brightness on kind of a strange negative scale. The more negative the number is, the brighter the object is going to be. In terms of this right here, write down that the sun has the largest apparent magnitude. The sun has the largest apparent magnitude. Obviously, the sun is the brightest thing in the sky. That's why it has the biggest apparent magnitude. Jupiter has a value of -2. The brightest star in the sky, Sirius, is -1. If you can pick out the North Star Polaris, that has an apparent magnitude of 2, which is still pretty bright. If you don't know how to find this star right now, you'll figure it out by the end of this class today. The faintest stars you can see where we are is apparent magnitude of 3. But if you're out in the country, you can see stars up to 6. The closest star to us is Proxima Centauri. It has an apparent magnitude of 11. So the question might be, why is it so dim? It's dim because it's real small. It's not putting off too much light. Even though it's real close to us, it's a pretty weak star. So that's apparent magnitude. The next thing we're going to talk about is things with respect to a star's spectrum and the light and the different colors that it gives off. So a spectroscope is something that basically takes light rays and it breaks the light rays up into the different colors of the spectrum. If you have something like this in a classroom, it would look sort of like this. They're pretty cheap. I used to have some till they broke. I got to get some more. But it takes those light rays and it breaks them up into the different colors of the spectrum. And if you point a spectroscope that is very scientific and very, very pricey at a star, you're going to see a spectrum of colors. But not only are you going to see a spectrum of colors, you're going to see these weird black lines going up and down too. So the question is, what do those lines mean? We call them absorption lines, and what you need to write down about those is write down, yeah, you got to write down something from this. Write down the first bullet point. Yeah, different elements absorb different wavelengths of colors. Yeah, you can title this part as absorption lines if you want. No. So do the first bullet point, also do the last one. That should be good. So when we see these black lines on the spectra of colors that come back from our spectrometers, you can use those in order to tell what elements are present on that star. You can actually tell then how hot that star is, because the hotter it is, the more of those elements are going to burn off. And if you have a star that has a whole bunch of elements, you can assume it's not very hot because it hasn't burnt away all those elements yet. So depending on where these lines show up, those correspond to different types of elements out there. And this one's on your handout. If you look at your stars and you have a black line that shows up right here, you know that star contains sodium. There's different places for titanium oxide. You've got a calcium line right here. And of course, hydrogen and helium, those are the two most prominent molecules out in the universe, so your stars are going to always have those. But it's kind of interesting that when you see these black lines, they actually mean something. They're not just there. So spectral class is the next thing that we need to talk about here. And when we talk about spectral class, we're basically talking about different colors of stars. And this is that same constellation we looked at from the first slide where I said there was one. This is Orion. And you can see he's got different colored stars in that whole constellation there. So you've got blue, you've got red, you've got yellow, and we divide those into these 7 categories. if you were looking for a way to memorize these, when I was in college, the acronym they used was, "Oh, be a fine girl, kiss me." So that's one way to kind of remember from hottest to coldest how those stars are. The hotter they are, the bluer they are. The more red a star appears, the cooler it's going to be. And these temperature differences are pretty massive, as you'll see. So these are different colors of different spectral types. What I'd like you to write down here is the second bullet point, along with its subpoint right there. Yep. The second bullet point, and then the little information by the hash mark there as well. So yeah, the different colors are what change your spectral type, and the bluer it is, the hotter it's going to be, the redder it is, the cooler it's going to be. And I mentioned this with the last bullet point here because depending on what stage a star is in, these sizes are going to be different. So if you have an O-type star that is kind of in the middle of its life, that's how big it would appear compared with the others. But if you have, say, a K-type star that's near the end of its life, it might actually be even bigger than this size. That's something we talk about later on. But yeah, these are sizes relative to stars that are not near death. This is on your handout. It gives you an idea of how hot some of these stars are in terms of their temperature in Fahrenheit. So these little M-type stars, these red ones, are actually pretty cool. I mean, 3,000 degrees to 6,000 degrees? That's only like, I don't know, 7 or 8 times pizza cooking temperature. Yeah. And this is a star. I mean, this isn't like a hot planet like Venus or anything. So this is actually pretty cool. Oh, I mean, this is a very hot place. You could cook a pizza in about 2 seconds with that temperature, and it would still come out burnt. So yeah, you get these different colored lines based on the different color stars. So what you can see here is that O-type stars have less elements than the M-type stars. So these cooler M-type stars have a lot more black lines. So that corresponds to more elements. And yeah, hotter stars have less elements because they've burned all the others away. Luminosity class is something we're going to talk about next. If you learn nothing else from this class, I want you to learn this right here, right now. How many people can find the North Star in the sky? Raise your hand. Just a few. That's going to change. How many of you know what the Big Dipper looks like? Okay, good. Yep. The Big Dipper is this guy right here. It's like a little spoon at the end of a curved, stick. So there's your dipper. If you want to find the North Star, you take the end of the dipper and you follow it in more or less a straight line, and it will point you exactly to the North Star. So your North Star is right here. You want to make sure that you take that with you. You don't have to write it down. But yeah, follow the end of the dipper, and if you follow it in a straight line, the next kind of bright star is the North Star. And the cool thing about that is that it never moves. The North Star is there even right now. It is right there. If you could see through the ceiling, the North Star would be right there. If it wasn't, if it wasn't too bright out, you'd be able to see it. All the stars revolve and rotate around that one. It's always in that exact spot. The reason for that is because as Earth spins, it's spinning on an axis, and that axis points exactly to that star. Yeah?
Can you also just look for the Little Dipper?
Yeah, if you can find the Little Dipper, yeah, it's the end of it. Some of these stars are kind of dim, though, so that can make it hard. But yeah, if you're at the North Pole, this is directly overhead. And the closer you get to the equator, the further towards the horizon this is going to be. Luminosity is what we're going to talk about next. Go ahead and write down this first bullet point.
Whoa.
So yeah, luminosity is basically a measurement of how much light something is actually giving off. You know, apparent magnitude is a measure of how much energy we're seeing from here on Earth. But of course, some of the brightest stars are super far away. And so it's, you know, how bright they appear to us here isn't really a good measurement of how much energy they're actually giving off. Luminosity takes that into account. It's basically saying if you were at a set distance, how much light would you be receiving? So the light bulb gives off 100 watts. You can see the sun gives off a lot more. And luminosity is measured as a ratio from the sun's luminosity. I mean, I couldn't. I mean, this would be million, billion, trillion. What is this, quadrillion?
Yeah.
Septillion?
Yeah.
Okay, so 400 septillion watts are coming off the sun and into our lives. All right. So in addition to these absorption lines being certain elements, when we look at those lines themselves, they tell us a little bit about the star's luminosity. And what I'd like you to write down from this is the first bullet point along with the two subpoints there. Yep, we're still on luminosity here. First one and then the two small ones after it. So yeah, you can tell a lot from these absorption lines, not just what elements are present on that star, but you can tell a little bit about the star itself. If you've got a nice wide line, that means that there are a lot of that element there. It's being absorbed quite a bit, and so that means it hasn't burned it off, so it's a smaller star. It's dim. Narrow lines, you've got bright, large, low-density stars. So make sure you know those distinctions. This is on your handout. We define luminosity classes in terms of Roman numerals, starting with 0, and then going on down to 5. 5 is going to be kind of your basic common stars, and as you ascend in this, you get larger stars that are out there. And we'll be talking about exactly how big these things are in a little while. It's kind of hard to imagine how large some of these stars can get, but we'll do our best. This is a picture right here of the largest star that we know of. This is UY Scuti. And it's not all that bright from the Earth. The reason it's not all that bright is just because it's so far away. If this was right where the sun is, we'd be engulfed and burned to a crisp long ago. So let's just see if you can follow me here, okay? Here we go. Here is Earth. We kind of have a general idea of how big Earth is, okay? So let's take Earth and let's shrink it down. Here are how big the outer planets are compared to Earth. So now what we're going to do is we're going to take the biggest one, Jupiter, we're going to shrink it down to this size. And this is right here, Proxima Centauri. This is the closest star to us. This is the sun. That's how big the sun would look compared to Jupiter. And this is Sirius, the brightest star in the sky. So now what we're going to do, we're going to take Sirius and break it down to that size. Now you've got some other stars that you don't need to know their names, but these stars are getting awfully big now. So now we're going to take Aldebaran and shrink it down to that size. And there's Rigel there. That's one of the stars in Orion's constellation. And then you've got Antares here. Betelgeuse, this is another star in Orion. And we shrink Betelgeuse down. And these are the largest stars that we've ever observed. So it's kind of difficult to imagine shrinking all those things down. But hopefully it gives you an idea of how big some of these places are. Again, our star is big. Our star is massive. This is our star compared with Jupiter. And when you compare Jupiter to how small Earth is, these are big places. So let's just look at this directly then. This here is not even the biggest star out there. And here's our sun by comparison. These things get awfully big. They do have a comparison of the largest star compared with our sun. And that's what this is right here. You got to zoom in pretty far to even see the sun. The sun's just 1 pixel if you zoom out far enough. You can barely see it right there. So yeah, our sun is tiny compared to some of the stars that are out there. Okay. So the next thing we need to do, if ultimately we're trying to figure out the absolute magnitude of these stars, is we have to put all this information, its spectral class and its luminosity class, on something called an HR diagram. And these are rather intimidating. It's on your handout, and you'll notice that it's a graph with 4 axes. It's not often you see a graph with 4 axes. So again, there's Orion. Go back one?
Can we go back to planets? I don't want to.
Nope, we're here to stay. So this is your HR diagram right here. We'll get to. I want to emphasize a couple things about that in just a second here. What I'd like you to write down about a star's absolute magnitude, though, is this first bullet point. Absolute magnitude, and then the first bullet point. Write that down, please. Yep, title and the first bullet point. So 10 parsecs is equal to 32.6 light years away. I forgot actually what a parsec is, what makes it significant. I'd have to look that up, admittedly. But basically what we're doing with absolute magnitude is we're saying, okay, let's place all the stars at this distance, and however much light we receive from that distance would be its absolute magnitude. So it's a true measurement of how much light these stars are giving off. So again, this is your HR diagram. And the reason there are 4 axes is because luminosity is a function of absolute magnitude. If you know how much light that star is giving off, you can figure out what its absolute magnitude is. Just like spectral class, if you know an object's spectral class, you can figure out its temperature and vice versa. If you know its temperature is 4,500 degrees, that corresponds to a particular spectral class. So they're all related here. So try not to get intimidated by the 4 axes. From this, go ahead and write down absolute magnitude, and the Milky Way is the highest absolute magnitude. Absolute magnitude, and that the Milky Way has the largest absolute magnitude. Yep.
The Milky Way is just a star.
Yeah, so this is kind of cheating. But if we're talking about everything that we see in the sky from here, yeah, the Milky Way would clean house just like our sun cleans house for apparent magnitude.
It's like if we were on a different planet, like outside the Milky Way, would the Milky Way just look like a giant star?
Basically, yeah, depending on how close we were to it. Because we can see other galaxies from here. Most of them are too far away to be real clear and visible. You can see 1 or 2 with your naked eyes and without a telescope. But yeah, UY Scuti would be -6, so that's pretty bright, and it kind of just gives you some of the other things. The sun would be very, very, very dim. You could only see the sun if you were in a very rural setting. So, we know how to get absolute magnitude now. It's by using that HR diagram, which we figured out based on how hot and what color those stars were and how much light they were giving off. Once we know absolute magnitude, we can figure out that star's distance. So, what you need to write down from this slide write down photometer, measure apparent brightness, spectroscope, measure luminosity. So yeah, the point here is that you have to know that in order to figure out how far away a star actually is from us, you're going to end up with a fancy looking equation, which is what that is. But in order to get there, in order to get that information, you need a photometer to measure the apparent brightness, how bright it appears on Earth, and you need a spectroscope to measure its luminosity, how bright it would appear from a set distance. And then when you have that information, you can plug it into that fancy equation, and out pops your distance. So just like all the planets, and just like all the moons that we looked at, they testify not to a universe that has been around for millions and billions of years. They testify to a universe that has been around much, much more recently. On this slide, go ahead and just write down the first bullet point, please. So the problem here then is that we've got tons and tons of galaxies that we've looked at through the Hubble telescope. And the ages of these galaxies are supposedly billions and billions of years. But there's no way blue, hot stars can last that long. They're super hot. They're using up their fuel extremely fast. There's no way they could last for those billions of years. And so the answer typically then from astrophysicists is that, well, those stars formed, more recently within that galaxy. But when you start talking about things like star formation, it is riddled with problems. Because in order to get a star to form, you somehow need gas and dust to somehow come together and coalesce on their own. And if you know anything about gases in general, that does not happen. If I gave everybody in this class a cigarette and we all started smoking, the whole room would be filled with smoke rather evenly. That smoke would not come together into little shapes and start forming balls that would eventually create stars. And so if it's not going to work on that small scale, it sure as heck isn't going to work on a big scale. When you talk about gases and the gas laws that we deal with in the real world, what goes on there is particles, when they're in gas form, expand. They go away from each other. They don't come together. That's not how the physics works. And so basically what they say is that somehow these stars formed. And if you're curious on other issues with star formation, I've got resources if you'd like to borrow them over a break at some point. But yeah, Neil deGrasse Tyson, who is pretty much the big scientist these days, says, the scary part is that if none of us knew in advance that stars exist, frontline research would offer plenty of convincing reasons for why stars could never form. And those convincing reasons are that they go against the gas laws in thermodynamics and physics.
Like, stars don't form, they're just already there. Right?
Yeah.
So what happens if, this might sound dumb, what happens if all the stars eventually burn out?
That's what they call a heat death, actually. That would be something where there's no stars left over in the universe, and everything would get really, really dim. But stars should last for a long period of time. It's not like these stars would die out in just a couple hundred years. The point is that they wouldn't last for billions.
Right.
And if you can't get stars to form, there's no way that they could still be in these massively old galaxies. To close out, I've got pretty pictures of stars. So sit back and enjoy. This is called the Rosette Nebula. It's actually part of the cluster I did my research on when I was in college. There we go. And this is another group of stars that I did research on. It's called the Christmas Tree Cluster. I think it's NGC 2264, something like that. Pretty cool looking stuff. And stars. The end.